Hello, ladies and gentlemen. Today we are going to watch a video that will further our instruction with rational functions and rational algebra. In the past we have learned about simplifying, multiplying, dividing, adding, and subtracting rational expressions using a variety of techniques. And today we will further that discussion by talking about complex fractions and how to apply a lot of these techniques together to make that possible. So first, what we'll do is talk about what a complex fraction is. A complex fraction is any fraction that contains either numerator or denominator, or in many cases both, with simple fractions in both parts. For purposes of today's discussion, we will see many examples where they have both a numerator and denominator with simple fractions, and in many cases multiple fractions within the numerator and the denominator. And there are two techniques that we will learn about that will allow us to simplify them, both using ideas that we have learned over the last few lessons. The first, if we look at the fact that a complex fraction is a fraction over a fraction. Keeping in mind that a fraction represents division, this is a fraction divided by a fraction. And since we don't use a technique where we divide, we use our stay, change, flip approach by converting it to multiplication. At that point, we will have many ways we can go ahead and simplify, either by multiplying across, simplifying and then multiplying across, or as we go into some more elaborate problems, we'll have to factor as well. The other technique is by identifying the least common denominator, which was part of our last discussion of addition and subtraction of fractions, and then using that idea to multiply through and canceling out all the individual denominators of the simple fractions. So what we're going to do is start looking at some examples, and our first example that we will look at, we will use both techniques to make sure that we are clear on the approach. Now let's go on and get started. So our first example, we see two fractions. Our first one is 1/4 divided by 3/8. If we go and use the stay, change, flip approach, the first fraction 1/4 remains the same. We change it to multiplication, and then we flip our second fraction to be 8/3. At this point, we do have two options. We can go ahead and multiply across, and we get 8/12. But that does need to be simplified, and when we cancel out a factor of 4, we get 2/3. Or if we needed to, we could see that there is a factor that does simplify ahead of time. We can simplify that to 2/1, all right, which leaves us with just 2/3 to begin with. So when it comes to simple fractions that are numeric in nature, either multiply and then simplify, or if you see any factors that simplify, you can go ahead and do that from the get-go. If we apply our second technique, where we take and identify the least common denominator, all we have to do is multiply both of these simple fractions by that common denominator. Our LCD in this case is 8. And when we look at it, the 4 and the 8 in the numerator cancel out, but leaves behind a factor of 2. And in the denominator, the 8's cancel each other out. And all you have left is 2 in the numerator and 3 in the denominator. To make the process a little simpler, you can do a combination of these approaches. By taking their fractions, and we look here at example number 2, there are 4 individual fractions. Identify and change the fractions to be over that common denominator. So here we have 4 fractions, 3, 5, 15, and 5 are our denominators, which means our LCD is going to be 15. Now, if you remember from our previous discussion, we only change the appearance of fractions by using multiplication. So for our first fraction, multiply the top and bottom by 5, gives us 5/15. In our second fraction, we need to multiply in a factor of 3, which is 6/15. In our denominator here, the nice thing is our first fraction is already over 15, but our last fraction is missing a factor of 3, so it's 9/15. Now, when you have two fractions that the same denominator is there, and you do your stay, change, flip, those denominators are going to cancel out. So to save ourselves a step, once we have all fractions over the same denominator, we can cancel out those denominators, and in our numerator we have 5 plus 6 remaining, in the denominator 4 minus 9. And once you cancel out those denominators, all you have to do is perform whatever operations are remaining that includes simplifying. Here we have 5 plus 6, which is 11, over 4 minus 9, which is -5. And that is your simplified answer. So this approach combines the two ideas of identifying your least common denominator and using the approach of stay, change, flip. If you have a common denominator and do stay, change, flip, they will always cancel each other out, so you can actually skip showing that step. One thing you do have to be aware of is that a lot of times when we get into our fractions, especially complex fractions, we will see that some fractions do not have a denominator present, but they still must be expressed over 1. So when we look at exercise number 3 here, we still technically have 4 fractions that we have to focus on. So what we're going to do is, looking at all 4 fractions here, let's identify what our common denominator is going to be. Well, these two are 1's and these two are x's, which makes identifying your common denominator here very straightforward. Our LCD in this case is going to be x. Now in the first fraction, when I multiply that x in, be careful, x times x is going to be x squared. The nice thing about our second fraction here is already over 1, or already over x, I apologize, so it stays as 1 over x. In our denominator here, again, we are missing a factor of x. X times 2 is 2x. And our last fraction here is already over x, so that numerator does not change. So again, using the idea of state change flip, we can say that our denominators are going to cancel out, so we can cancel them out. And we write down what's remaining, which is x squared minus 1 in our numerators over 2x minus 2 remaining in our denominators. And if we think back to our discussion a few lessons ago, anytime we have a rational expression, we must look to cancel out common factors. Key word in all that is factor. So before we cancel anything out, we have to make sure we go through our factoring approaches. In numerator, there is no GCF, but we do have a difference of squares. In our denominator, there is a GCF of 2. So when I look at my factored form of my rational expression, I see two binomials that are exactly the same factor, which means they do cancel out, and I'm left with a simplified rational expression of x plus 1 over 2. Now, as we progress through these three problems, the amount of work obviously has intensified. Now, before we go on to the next slide, if you need a moment to catch up on any notes, please pause the video now. Okay. As we go on to the next set of problems, we start looking at, again, complex fractions with 4 individual simple fractions. So as far as a technique goes, we will look and try to identify the common denominator for all 4 simple fractions. And here we have denominators of x and 5 and x. And when you have a number and a variable, the only real way to identify a common denominator is to just put the two together. So our LCD in this case is going to be 5x. Which makes multiplying here to change our fractions very straightforward. It either has a 5 or an x, so we have to put in the other factor. So in our first fraction here, we are missing the 5. 5 times 2 gives us 10 over 5x. In our second fraction, we're missing the x. 3 times x is 3x. As we shift to our denominator fractions, again we see that the first one is missing the x, so 4 times x is 4x. And our last fraction is missing the 5. 3 times 5 is 15. So again, once you have changed all 4 fractions, all 4 individual simple fractions to be over that common denominator, the state change flip approach will cancel them out, so we can go ahead and do that, and we write down what is remaining. We have 10 minus 3x remaining in the numerator, and then 4x plus 15 in the denominator. Now again, once you have these binomials or any rational expression containing variables, the only way we can simplify is by canceling out common factors. Now when we look at this, it is tempting to say that the 10 and the 15 do simplify to 2/3. However, this 10 is connected to minus 3x, and this 15 is connected to the 4x. So these are not individual values, they are part of a bigger set of factors. Now 10 minus 3x, there is no GCF, it is not a difference of squares, so there are no factors there. And then likewise in our denominator, there is nothing to factor there. Since neither part factors, there is no chance for any factors to cancel out, so by default, that is our simplified expression. So sometimes once you cancel out your denominators and you write down what's left, there is nothing left to simplify, and you already have your simplest form of your rational expression. As we saw on the front, on the last problem, however, sometimes we do have to factor, so always keep on the lookout for that. And when we go on to number 5, again, we see that same setup as the 2 problems ago, where we have 2 fractions that are not expressed with denominators, but again, keep in mind that they do represent individual simple fractions that you have to change to match whatever your LCD is going to be. Now, when I look at these 4 fractions, there's only one real denominator there, that is b, which makes identifying what your LCD in this case is going to be very straightforward. Now the first fraction is already over is already over b, so it will remain as a over b. Now when it comes to a fraction that's 1, remember the nice rule about division. Your numerator and your denominator need to be the same, otherwise it won't divide to 1. So b over b becomes our second fraction. Our third fraction is already over b, so again we'll just carry that down as is, a squared over b. And our last fraction here is missing the b as well. b times b is b squared. So again, we have changed all individual simple fractions to be over the same denominator, so based on state change flip, they will cancel out. You have a plus b remaining in the numerator, and then a squared minus b remaining in the denominator. But again, anytime you have an expression that is a simple fraction, make sure you look to see if it simplifies. A plus b, there is no GCF. It is not a difference of squares. It does not factor. But when I get to my denominator here, there's still no GCF, but this is a difference of squares, which makes it a little tougher to visualize because of the two variables, but we can factor it to our set of conjugates, a plus b and a minus b. Now when I'm carefully crossing off my common factor of a plus b, I notice that my entire numerator cancels out, and the only factor that is remaining is a minus b, and it is very tempting to say that the simplified answer here is a minus b. Unfortunately, that would be incorrect. When I look at the placement of a minus b, it exists in the denominator of the fraction. That can't change. So anytime your entire numerator is canceled out, you must express it as 1 over whatever remains in our denominator. So our simplified answer in this particular case is 1 over a minus b. So just be aware that anytime your numerator cancels out, you still have a fraction remaining as an answer. Your numerator is just 1. Now when we shift on to number 6, it is possible to see a complex fraction that contains 5 individual simple fractions. It doesn't change the process. We still have to identify our common denominator. It just means now we have to do it with 5 fractions instead of 4, 3, or 2. Now in the numerator we see a 6, an x, and an x squared, and then another x and an x squared in the denominator. So our LCD in this case is going to be 6x squared. So I'm going to change all 5 of my fractions to be over 6x squared. Now since none of the individual simple fractions have 6x squared as our denominator, we do have to change all 5 of them. So our first one here is missing the x squared. X squared times 1 is x squared. In the denominator of the first fraction, there's a 6 and an x, just missing one of the x's. 5 times x is our second numerator. And our third fraction has the x squared in the denominator, is just missing the 6. 6 times 1 is 6. Now we shift to the bottom, and the toughest one of all 5 of these to change is our fourth one here. This one is missing the 6 and one of the x's, so it actually is missing 2 of the factors. 6x times 1 is 6x. And then our last fraction here is just missing the 6. 6 times 1 is 6. So the process itself has not changed. We just ended up with 5 fractions that all have the same denominator that we now can cancel out based on state change flip. And when I write down what is remaining, I have x squared plus 5x minus 6 remaining in my numerator, and in my denominator 6x minus 6 remaining. So again, I am down to a single rational expression, and anytime that is happening, we must look to see if it factors first and then cancel out any common factors that exist. Again, it's tempting here to see that the negative 6's are in common and cross them off, but those negative 6's are attached to other components. So when I look at my numerator, I have a normal trinomial with a leading coefficient of 1, so I look for factors of negative 6 that add up to positive 5, which is x plus 6 and x minus 1. When I look at my denominator and go through my proper factoring techniques, I have a GCF of 6, which leaves me with a binomial of x minus 1. So I do have common factors of x minus 1, which leaves me with x plus 6 in the numerator and 6 in the denominator. And again, it's tempting to look there and see the two 6's and cancel them out. However, that 6 in the numerator is not 6. It is connected to the x. So we have a result, a simplified rational expression of x plus 6 over 6. If you need time to catch up on these notes, please pause the video now before I clear the screen. Okay, as we continue on to our next set of problems, we start off with an example where our denominator technically is not a fraction, but because of our technique here, if we're going to follow the same order, we must make it a fraction so we can identify what our LCD is and create all simple fractions to be over that common denominator. Now the nice thing is in this particular case, there's only one real denominator here, and it's a factor of 2, which means both of my simple fractions in the numerator are ready to go. We get x over 2 and 1 over 2 in the numerator. But what I need to be careful about is when I multiply that bottom fraction by 2, it does have to distribute through to get 2x squared minus 2. So again, we have our 2 fractions in the numerator, our 1 fraction in the denominator all over 2, so they cancel out via state change flip. I have a factor of x plus 1 in the numerator, and then 2x squared minus 2 in the denominator. Now x plus 1 itself doesn't factor. There's no GCF, it's not a difference of squares, but our denominator here is going to take 2 steps of factoring. First, a GCF of 2, which leaves me with x squared minus 1. But that in itself is also a difference of squares. So don't forget to keep carrying down the 2, and then you have your set of conjugates of x plus 1 and x minus 1. Now, again, we run into that situation from a few problems ago where our entire numerator cancels out. So we end up with 1 over, right? Your fraction does not completely disappear if your numerator's gone, and you have a factor of 2 and a factor of x minus 1 remaining. And technically, this will be acceptable as a simplified answer. If you decide you want to multiply those values together, that is distribution. So 1 over 2x minus 2 would also be an acceptable simplified answer of this complex fraction. Both of these are good. They have all common factors canceled out. It's just a matter of expressing their denominator in factored form or in multiplied form, both of which are fine. Okay. In number 8, we see two values that are both 1. And again, remember, any value that you see here needs to be written as a fraction so you can remember to identify its LCD and change the fraction accordingly. And again, if you remember from a couple of problems ago, what's nice about a value of 1, your numerator and denominator have to be the same to divide to equal 1. So what's nice is that whatever we identify our LCD, the numerator is going to become that value by default. So again, if we go through our process correctly, we still should recognize that we have 4 individual simple fractions here with an LCD of a squared. So we write our 4 fractions all over a squared, and the first fraction itself is already over that, which is nice. Now the next two, so the last one in the numerator and the first one in the denominator, are both 1s. So your numerator and denominator need to be the same in order to divide to equal 1, which means LCD over LCD, a squared over a squared over a squared. But our last fraction a little bit missing. We're missing one of the factors of a, so we multiply that in, and you get a over a squared. So there's a lot of a's here, but again, the ultimate goal was to cancel out our common denominator through state change flip, and we write down what's remaining. We get 1 minus a squared over a squared minus a. Now, despite the order, even though we're normally accustomed to having our variable first, subtraction is important. This identifies it as a difference of perfect squares, but because subtraction is not commutative, we must remain in that order. So when I factor to my set of conjugates here, I get 1 plus a and 1 minus a. In the denominator, we go through our normal factoring techniques. We identify a GCF of a, and we get a minus 1 as a remaining factor. And if we go back to our discussion a couple of days ago, subtraction, remember, is not commutative, but there is a way that we can simplify and cancel out this factor. They don't cancel out completely. It leaves behind a factor of negative 1. It is the only exception to that rule about binomials being exactly the same, because they're not canceling them out completely. It's that negative 1 factor that makes that possible. So the next question is, where does it go? And we have choices. We can put it in the denominator with the a. We could put it in the numerator with the 1 plus a. Do not do both because they cancel each other out. So you can end up with 1 plus a over negative a as an example. Or you can even just put it in front of the entire fraction and negate the entire value. So negative of 1 plus a over a. So you do have some choices about where you want to place that a. That negative 1 with the a or the numerator or in front of the entire fraction. Just be consistent. All right, and do any multiplication with that negative wherever you decide you want to place it. Okay, pause this video if you need to catch up on your notes before I clear the screen. Okay, and as we move on to our last discussion on complex fractions, all right, there are a few more that we didn't focus on, sometimes containing multiple variables. And we look here at number 9, we see that we have 5 individual simple fractions with multiple variables, so identifying our LCD becomes a little trickier. So when we look at all 5 of our fractions here, we see that there's a squareds, ab's, b squareds. So when we put them together with the proper exponents, our LCD is going to be a squared, b squared. Now some of these fractions are going to change a little easier than others, especially when we get into our denominator here. We have to be very careful that we match up the proper amount to pair up with our LCD. Our first fraction, a squared, missing factor, so we get a squared over a squared b squared. Our denominator is missing one of each, so 2ab, we multiply it in, becomes our second numerator. And our third fraction in the numerator is missing the b squared. The 2 on the bottom is where we need to be very careful. Our first one in the denominator has one of the a values. So we're missing an a, but both b's. So ab squared becomes our numerator value. And likewise, our last remaining fraction in the denominator has one of the b's, but is missing both a's. So we need to multiply a squared b into our numerators. Now that required a lot of work. A lot of variables were written down to create our least common denominator. But through state change flip, they do cancel out. Just be careful not losing any signs as you write down what is remaining. So we have a squared minus 2ab plus b squared all over ab squared minus a squared b. Now remember, when it comes to our simple rational expression, in terms of simplifying, remember, we need to cancel out common factors. The fact that there's a lot of a's and b's here, becomes very tempting to start crossing things out. Now in terms of our trinomial, normal factoring, factors of 1 that add up to -2 are -1 and -1. So but instead of a minus 1, we have that second variable b tossed in there. So our factors become a minus b and a minus b. Our denominator is a GCF approach. There's an a and a b in both terms. And when I pull that out, I have a b minus a value remaining. And again, just like last problem, we have that same value remaining where we have subtraction in reverse order. We can cancel them out. Don't forget that does leave behind a factor of -1. So be careful where you decide you want to place it. If you want to put it in the denominator, we have -ab. If you want to place it in front of the entire rational expression, your fraction is negative. But remember, do not put it in two different locations because then in the end you're canceling out the negatives with each other. And we have our simplified answer of either a minus b over -ab or the negation of a minus b over ab. As we saw with addition and subtraction in our last lesson, sometimes having to identify common denominators involves factoring your denominator to see what factors actually exist. So in our last denominator here we see x squared minus 4, which is a difference of squares. So when we look at that as x squared minus 4, we actually should consider it as a set of conjugates, x plus 2 and x minus 2, which is nice because those are the individual denominators that we do see in the numerator. So there's not going to be much to change as far as identifying our LCD. If you remember our LCD, our rule that we're going to want to follow, if we see it in a denominator, we keep it in our common denominator, which means our LCD is going to be x plus 2 and x minus 2. And because of the state change flip canceling them out, if you decide you want to write them as x squared minus 4 or x plus 2 and x minus 2, either is fine because they will cancel out in the next step anyway. Since our denominator already had the x squared minus 4 or both sets of binomials, there's nothing to change there. But what we do need to be careful about when we multiply in that missing binomial, in the first case it's x minus 2, we do have to remember that distribution is always going to take a part when a binomial is being presented into a fraction. So when I distribute the 3 through that missing factor x minus 2, our numerator becomes 3x minus 6. Our last fraction here we get 4, that's already there, with the x plus 2. Now we are going to have to be careful in this particular problem because not only are we going to have another distribution, but when I cancel out my denominators there is subtraction between them, so be very careful about our signs. So through state change flip we cancel out our common denominators. And because of the fact that we have binomials, I'm going to keep our numerators in parentheses to remind ourselves that when we go ahead and combine our terms here, it is still through subtraction. Now the nice thing is, once we get down to our single fraction, the numerator in our denominator was a 1, which means there is no more fraction to simplify. We do have to combine terms carefully. So when we simplify, 3x minus 4x is -1x. And then this is where we have to be careful, and this is easy to lose the negative on. -6 minus 8 gives us -14. And again, because our denominator was 1, we don't have to worry about expressing it as a fraction or look for any further simplifying. Before I clear the screen, if you need to catch up on notes, please pause the video now. Okay, and we look at our last two problems here. Initially they present themselves as just normal fractions, so we don't see that complex fraction setup that we've been working on the last group of problems. But what we do need to keep in mind is that we do have some negative powers. Now we've seen these on and off throughout the year. What we need to remember is that a negative exponent takes the reciprocal of your base and then makes the exponent positive. So even though initially it presents as a normal fraction, there are multiple negative powers that will result in individual simple fractions. So as I go through the fraction itself, our first term, 4 over 1, there is no power attached to it at all, never mind a negative, so we'll just keep it as 4 over 1. A to the negative second power, when we apply that negative power, becomes 1 over a squared. Now we have to be careful about that first term in the denominator. The 2 is not attached to the exponent, otherwise you would see a set of parentheses around it, so the 2 itself is not going to change. It's just the a that gets moved down to the denominator, which gives us 2 over a. And again, our last term here, we have a to the negative second, which is 1 over a squared. So by taking care of all of those negative powers, that is what gives us the result that is a complex fraction. And now we can apply the same technique that we've been working on. So we have 4 simple fractions that we need to identify our LCD for, which happens to be a squared. So as I go through each individual fraction, the first one, I see that there's nothing there. It's a denominator of 1. So we are missing the complete a squared. Multiply that by the 4 that's there. Our numerator becomes 4a squared. The nice thing about our second fraction, it already is over our LCD, so it will remain as 1 over a squared. In the denominator, our first fraction is just missing one of the a's, so we multiply that through and we get 2a. And our last remaining fraction, again, already over our LCD, so it just stays as 1 over a squared. So, through state change flip, those cancel out, and we have remaining 4a squared minus 1 in our numerator, and 2a minus 1 in our denominator. So again, once we reach that point where we're at a simple, single, rational expression, we must look for factoring. No GCF in either cases, but this is a difference of squares in our numerator. So our set of conjugates, 2a plus 1 and 2a minus 1. But we don't have to worry about doing any of that in the denominator. 2a minus 1, there is no GCF. It is not a difference of squares, but I should already see that the 2a minus 1 is going to cancel out with the numerator itself. Now the nice thing about this rational expression is the entire denominator cancels out, which means in itself there is no fraction remaining. So 2a plus 1 is your simplified rational value. In our last example that we're going to cover today, again we see our negative powers. So again, individually you take each expression, being careful about what actually has the negative exponent attached to it. So for our first fraction here, 6 doesn't move. Likewise, the 3 in our second value, so we get 3 over x squared. In the denominator, 2 to the negative first power just becomes 1/2. And then that last value, no exponent, no fraction to worry about, but make sure you express it over 1 to remind you that it is a fraction that we need to get a common denominator for. So again, once we take care of those exponents, we result in a complex fraction that we've been working on. Looking through, we identify our LCD, 2x squared. And we go through using our proper arithmetic to change all of the fractions accordingly. So the first fraction is missing the 2 and the x, so we multiply that through, which gives us 12x. Second fraction, just missing a factor of 2. 3 times 2 is 6. In the denominator, missing the x squared. 1 times x squared gives us x squared over 2x squared. And our last fraction is actually missing everything. Just be careful of our multiplication here, that when you're multiplying the 2x squared, we end up with 2x cubed as our numerator. So, through state change flip, cancels out. When we get 12x plus 6 in the numerator, x squared plus 2x cubed in the denominator. Now that's our single rational expression, but anytime that we get that as a result, we must always look to see if it simplifies. Now through proper factoring techniques, we see that it's a GCF of 6 with a remaining binomial of 2x plus 1, which doesn't factor any further. And in the denominator, we see a GCF of x squared, which leaves us with 1 plus 2x. Now, just like we saw for a couple problems, we see a binomial backwards. But what's different about this particular set of binomials is that addition is commutative. And we see, and hopefully remember, that these two are the same factor. So they do cancel out completely without leaving behind a negative factor. So our simplified value is 6 over x squared. Before we finish up, if you need time to catch up on notes, please pause the video now. So through to this video, we learned how to simplify complex fractions through a variety of techniques. by identifying the least common denominator and using our division rule of state change flip to cancel out common factors. Make sure in the end that when you are done that your individual single fraction is simplified completely and then all common factors have been canceled out. Again, that usually implies that you're going to have to factor any binomial or larger that you see in order to see those similar factors that 2 cancel out. As we move on to tomorrow's lesson, we will continue on and tie together many ideas that will involve rational fractions, and we'll move on to solving. Thank you for watching.